right, so welcome back to week 7 now, wow, of Physics 325. We're talking about diffraction this week. And we've talked about interference last week. Interference is when we had 2, maybe 3 beams that were coming together and we had destructive or constructive interference. And when we did that, we saw rapid variations in the intensity. Now, if we have 10, 1,000, a billion, or a continuum of waves, we still have interference. Light is an electromagnetic wave, but we talk about it a little bit differently. Specifically, that's usually what we call diffraction. So the general setup is that we're going to have a continuum of waves, a distribution of waves, and we're going to look at how it propagates. And diffraction is what allows light to, as it is sometimes said, bend around corners or spread out. You might have seen this in your lab already, that when we had a single slit or a double slit, we confined the light to a very narrow region. And in doing so, we found that it spread out. And the more we tried to squeeze it in, the more it spread out over space. This is diffraction. And that means that there's some, or it hints at least, that there's some relation between the spread in angles, the spread in directions, and the spread in space. In fact, there is. They're inversely proportional relation. So the product of the spreads of the distance rather, and the spread in angles is a constant. We've seen this already with time. Frequency and time had the same relation. And as such, we're going to actually be able to treat this as Fourier pairs. And that's what we're going to build up to today. But the first thing we're going to talk about is diffraction, and the fact that, well, diffraction is complicated. Diffraction is a very complicated phenomenon. In fact, it's so complicated that analytically, if we just treat light as a wave, three-dimensional wave, it's only been solved analytically perfectly for a few very simple geometries, like a perfectly conducting wire or a half plane. And so it is a very complicated problem. The general problem of diffraction can be stated as follows. Given the field at one location, what is the field elsewhere? All right, and this is why it's difficult, because light's this three-dimensional vector field, and if we have this continuum of sources, we have to add them all up and take them all into account. So we're going to make a few simplifications in the typical approximations of optics when light is going along a particular direction. We're going to assume that light is in the paraxial approximation. That is, it's mostly going along one direction, usually we call it Z, with slight angles up and down, or left and right. And we're also going to ignore the vector nature of light again. Light is polarized in one direction. We'll just solve the equations for that polarization, and that would allow us to apply the scalar approximations. So now our problem is a bit more tractable. So we're actually really looking at the field downstream, a distance Z later. And now I can say, given the light distribution in a plane, which is in the coordinates x prime and y prime here, given those that distribution in that plane, what is a field in a plane that is parallel to that, but just some distance Z away? And that's the problem we're going to solve. So it's going to look a bit simpler, right? We're going to assume we have plane waves like this, and we're just going to play with the functions that talk about how that field is distributed. Now, unfortunately, it's still a fairly complicated problem. It's still a tough thing to solve, okay? So in order to really hammer this down, it turns out that when we do this, we actually have to solve some messy integrals. And so we're going to pull out a trick to help us out, a trick that was called the Huygens Principle that was invented a long time ago in optics. And it says the somewhat counterintuitive fact that I can treat any wave that is propagating through space as if it was made out of a distribution of small spherical wave emitters. This is what the Huygens Principle says. Now, it's a little bit tricky. If light is going through vacuum, there's no atoms that can emit these spherical waves. Yet, mathematically, this works out perfectly fine. So it's a convenient way of treating light that's going to serve us very well in deriving this, although it may not correspond directly to reality. I do like it, though. I like it for another reason, is that it kind of predicts this picture that we had of light going through something like glass. And remember those little dipoles that were all emitting their own field? Well, dipoles, if you get far enough away, have these spherical wavefronts. And this Huygens principle explains that well, as if we had a bunch of little emitters. So it's not super intuitive, but it works out mathematically, and we're going to use it. Now, if you'll remember, back to assignment 1, I made you all solve for what is called a paraxial spherical wave. Not just because I'm a mean guy, but because I knew that we were going to use it, and we're going to use it now. So here's our expression for our paraxial spherical wave, okay? Our spherical wave in the paraxial approximation. we ignored the curvature in the denominator, and we were able to write it just this way. So in the assignment, we solved it for having an origin at xy is equal to 0, 0. And we're going to do something similar here. We have the origin at that plane, the z equals 0 plane, but we're interested in a distributed source. We're interested in the field along that plane. So we're just going to rewrite this equation in terms of having an origin at x prime, y prime. And these are the coordinates we get. So each Huygens wavelet, each point along this yellow distribution here at z is equal to 0, each point there is going to emit a wavelet of this form, okay? And this is the general setup, okay? Well, let's actually use this. Now we can start zeroing in on the problem of diffraction, of figuring out what the field is a distance later, right? This is going to be deriving what we call the Fresnel diffraction integral. And what we do is we take all those spherical wave emitters, and we assume that that plane, that z equals 0 plane, has a distribution of them. They each have their own weights. We're going to describe the weights of that function, which we call the aperture function, as E0 of x prime, y prime, all right? And this is just mathematically writing down what we can see in this picture, is that we just basically need to sum them all up to find out what happens at a given point in this plane some distance away. Okay, so we have our spherical wavelets, and the plane some distance away is then really just given by integrating out all those points along the x prime, y prime plane. So a few points to this, there's some terms out front, and where this comes from really is saying, let's just let our aperture be all of space. Like let's let the whole thing be a plane wave. If that's just a constant, if it's equal to 1, we should get a plane wave just some distance later. We already know that from what happens when we send a single wave through. It just is just a plane wave that propagates. So plugging in that condition, we get our normalization out front. All right, and we're going to just play with this f of xy, an aperture function. Just as a preview, what is that aperture function? Well, maybe it's our double slit, right? Maybe it's two rectangles that look like this, or maybe it's the pupil of your eye, or maybe it's some blob or a Gaussian distribution of electric field. It can really be anything. It's just described by that f of x prime, y prime. But remember, we're going to apply the Paraxial approximation. So let's do that. We haven't really made use of the Paraxial approximation yet. So what we're going to do is concentrate on that term in the exponent and see what we can get out of it. So we have this x minus x prime all squared plus y minus y prime all squared. And that's what that term actually looks like. The x prime squared plus y prime squared, that's just the radial distance away from the origin along your aperture plane, your z equals 0, where the light is coming from, right? So we'll just call that rho prime squared, right? Similarly, if you see up there, we have the distance away from the origin in the plane that we're actually interested in some distance later. We'll call that rho squared. And what's nice about this is we're integrating along x prime, y prime, the primed coordinates, so we can pull that directly out of the integral, and that's going to help us a lot. And then we just have these extra phase terms in the middle that we have to deal with. So just pulling that out of the integral and writing it this way, we see that we have our integral here. Okay, so let's make these cross terms a bit simpler. I want to have a quick look at them. So we have this term here. We have 1 over 2z. And in here we have minus x prime. So let's just pull this minus out. Plus y prime. And there's a k out here as well. Okay, so let's rewrite this in a different way when we think about what this actually means. Remember, when we had light in the Paraxial approximation at a small angle, we had some overall k vector, k, and the magnitude of that is what it has been from the beginning of the course, 2 pi over lambda, and we had a kx here, a kx, and that's equal to k times sine theta, and this was equal to k cos theta, and sine theta in the small angle approximation, in our paraxial approximation, is approximately equal to tan theta, it's approximately equal to theta, right? So we can approximate this as x over z, it turns out. Why? Because if I have a k vector, or a direction, which is just going here, so I have z this way, x this way, right? This is the beam that would be resulting from this k vector. Theta is approximately equal to x over z. All right, so this kx is equal to kx over z. All right, but that's actually very similar to something we have here. And by the way, there's a 2 here, wasn't there? I'm sorry, there's a 2 here. So let's see what we can do there. So if we just concentrate on this x part here, we're going to get, let's just pull it in. We're going to get a minus, the 2's will cancel, so we're going to get k times x over z times x prime, which we call kx x prime. All right, so this kx, remember this k was just the spatial frequency along the direction, and kx was the spatial frequency in the transverse direction, up and down in the k direction here. So we can actually write this as just the spatial frequency times the space, kx prime k, and that's written right here. Similarly for y, we can do the exact same thing. But this is actually a very illuminating way of writing this, okay? So we can actually write this integral in terms of kx and ky, which are the spatial frequencies. Let's do that. And all this junk out front, it's just a constant, and we're just going to call it a naught for now, just to keep our math clean. We can plug it back in whenever we want. And let's write what we have here. So look at this equation. We've greatly simplified the expression for the field some distance z away. So we integrate over the aperture function f of xy, the circle or square, or whatever the shape of our field is at z equals 0. We integrate over that whole thing times the field strength through there, and we just apply these phase factors. Okay, so for each plane wave, we're going to apply the plane wave might be at some angle. Okay, so for each plane wave, say we're going to a point here, that's going to correspond to a given plane wave. It's going to have some angle with respect to x, so it's going to have a kx and a ky. We multiply, we integrate this over all the angles that get to that point. That's what we're doing here. You see that? And that's just given by the spatial frequency kx times x and the spatial frequency along y, ky times y. That's directly in this integral right here. All right? And then there's this overall phase term. And we mentioned this on the assignment. We didn't go into too much detail. But what the phase term was, running out of colors here, it corresponded to the fact that there was a bit of curvature to these wavefronts, because if they started from a point, there'd be a bit of curvature remaining from these Huygens wavelets that we are integrating over, right? And that's that rho prime squared term, all right? This is very, very nice though, because if we look at this, if we remember way back 2 weeks ago, this is actually the almost Fourier transform, the technical term, the almost Fourier transform of f. In fact, it is the Fourier transform of the function times this quadratic phase, all right? So let's actually go a bit further. Let's look sufficiently far away. We're going to look far away from the field such that that curvature is negligible. And remember from assignment 1, we worked out the math that we found that for a certain condition, we could neglect the curvature there. Let's work in that regime. So let's just write down the integral. I haven't changed anything yet. We've just noted that this is really the Fourier transform of the function f of x, the aperture function, times this quadratic phase, which is a thing of beauty, actually. That's like, because we can compute that numerically super, super quickly, right? And we're going to work in the far field, and we're going to note that very, very far away, this angle is very, very small, all right? And our intuition is that that this angle should be very small if we're far away. But we've got to be a bit careful, because remember k is pretty big sometimes. It's 2 pi over lambda. So lambda is, maybe just under 10 to the 6, just under a micron for a red light, half a micron maybe. So that's going to be like a couple times 10 to the 6. So it's a very large number. So we might have to go far away in order to be in the far field. But we're going to go far enough away such that angle is very, very small. And therefore, these quadratic terms, what is this quadratic term again? Remember, rho prime is equal to, squared is equal to x prime squared plus y prime squared. Then we had a 2z here. And we all times that by k. So let's just think about under what conditions is this small. Let's just look along one direction, say x. We want this term x squared over 2z times k, which is 2 pi over lambda. We want that to be much less than 1, much less than any of these phases. Now it should be, if x is small compared to z, then x squared is very small. But k is big, so we have to be a bit careful. So let's just write down formally what that condition would be. Normally, x is called a, the distance, because it doesn't matter if it's x or y. So that means that a squared over lambda z should be much less than 1. And there's a fancy $10 word for that. It's called the Fresnel number. We want a very, very small Fresnel number. And as long as that's small, then we can neglect that quadratic term in our integral. And if we can neglect the rho squared term, we're in pretty good shape, because then it's just the Fourier transform of our aperture. The Fourier transform of this shape, whatever that shape is, gives you what the field looks like downstream, which is awesome. So let's look at that condition and relate the two concepts. So we have that we look at that Fresnel diffraction integral, this general case of diffraction, under the condition that we have a small Fresnel number, such that that term here, whatever basically the area of your aperture divided by the wavelength times z, as long as that's much less than 1, we can neglect that term and we get an expression for the far field distribution pattern. This is great. This is like the basis of all diffraction theory. What we see a distance away when we have a distribution of light, as long as this condition holds, is just the Fourier transform of it. So if I know how to take the Fourier transform of a square, which we'll do, then if I have a like little square cutout and I shine light through it, some distance away, I'm just going to get the Fourier transform of that square, which is something that we can compute without too much trouble. Same with a pinhole. I poke a little hole through some tin foil and shine a light through it. What I see in the far field is the Fourier transform of a circle, and we'll see that as well. And whenever this condition holds, a small Fresnel number, we call this Fraunhofer diffraction. Fraunhofer diffraction is what we see in the far field. Now, we can still compute the integral. We can still compute the integral by including that phase term, that quadratic phase rho, and we just call it Fresnel diffraction there, and it looks a little bit different. So it's not the Fourier transform of this, it's the Fourier transform of this thing times that e to the I rho squared over 2z term. We just got a different shape, so it looks a bit different, very close to the aperture than it does when you get some distance far away. I'll show you an animation which covers both cases just by always keeping the quadratic term in there. I'll show you that at the end of the lecture. Okay, so let's just do a few examples. All right, so first of all, my favorite one, a single slit. A single slit, what is that? It's essentially it's a one-dimensional problem, right? It's constant along y, say, and it's along x, you get no light through, then like all of a sudden all the light through, and no light for some region here, right? This is what our transmission. It turns out we've already calculated this. It's a sinc function, but let's just go through the exercise one more time. And we'll do it very roughly, because you've already done it, but basically, if I just look at the Fourier transform of this thing, it's essentially 1D, so I'm going to get our general expression for our Fourier transform, e to the minus I kxx plus ky y prime dx prime dy prime. All right, so that's going to go, the y's are going to integrate out. It's going to give us a constant out front. That's what that normalization did for us. So this is going to be directly proportional to the integral of this thing, and that's 0 almost everywhere except for a small region. So minus a over 2 times a over 2 of just 1. That's or E naught, we'll call it. Whatever the intensity is here. So this is what the field looks like for a slit, for a small, we take a razor and cut through a opaque black surface, shine light through it, and this is what this is describing. And then we just have this term here. So we're going to have our e to the minus I kx times x dx prime. And this is something we've done before. Let's do it. Easy enough integral to compute. So we're going to get 1 over minus I times kx times e naught here. And we integrate this thing. So times the integrand here. So it's going to be e to the minus I kx times a over 2 minus e to the plus minus minus gives us a plus a over 2 plus, right? Said one thing and wrote another. And let's do ourselves a favor. Bring this I inside and switch the negative in there. So that gives us that, and we'll go 2 over 2. Why do I do all this gymnastics here? Because this is one of our favorite identities, the second favorite identity of the course. E to the ix minus e to the minus ix over 2I is equal to sine. And if we have e to the ix plus e to the minus ix over 2, we get cos. So this is just sine of kxa over 2. Okay. So we have e naught times sine of kx, I better move this down a bit, times, what is it again? E naught times sine of kx times a over 2. And we have this kx here. And we can pull out an over 2 here. This is almost the same thing as in the argument, so I'm just going to multiply top and bottom by a. And I have a times e naught sinc sine x over x of 1/2 kx times a. And this is the field as we see it. I is just the field squared, so it's going to give us something very similar. Except it just never goes zero. No, it never goes to 0. So this is what we'll see. And this is just numerically calculating the Fourier transform on my computer in Python. This is the intensity pattern that we're actually going to find. So just this is in k space. This is in terms of k. So just to this is a very confusing part at first, or a potential pitfall, we'll say. We just found I in terms of k. So what we actually found was I times kx. I of kx, a function of kx, was equal to I naught times a. I want to bring all those constants out there, times sinc of a over 2 times kx. But that's kx. What is kx? Remember, kx is equal to k units of inverse meters times sine theta. So this is really a function of theta. This gives us the angular distribution, all right? Not a big deal, because we can easily convert it. Remember, we're in the paraxial approximation, so theta is just our distance away, however far away we are, over z. So this is equal to k x times sine theta, which is x over z. All right, that's our argument of what goes in there. X over z. So this sinc function, if we want I of x, for example, how much physical distance it is up or down, not a big deal. We just replace kx here. Oh, I put kx, sorry. So we replace kx with k over z times x. So this is actually equal to I naught sinc of 1/2 times a times k over z, which is our 2 pi over lambda. Let's just write that out, actually. Why not? 1/2 a times 2 pi over lambda. That's k times x over z. All right, and this is equal to I naught times sinc of pi times a over z times x. Okay, so we can write it in terms of actual space too, but the Fourier transform, just something to keep in mind, the Fourier transform gives us the angular distribution. It gives us the function in terms of theta, or equivalently in terms of kx. And we just need to do this substitution to find out how much actual physical displacement that corresponds to. And out of the corner of my eye, you have probably noticed it, there's a lambda that I was just missing. So some distance L away, we'll call it L, not just N, say we're L away from the slit, and this is the source here, some large distance away, we get like a spatial pattern that is still a sinc function, it just looks like this. All right, so we can actually make that substitution there. So this is what it looks like. Now you probably don't see this if you look in the lab. Why do you not see this? Well, typically when we do these experiments nowadays, we do it with one of these fancy old lasers here. And the laser does not have infinite height. So we actually illuminate it not in terms of this infinite height, but just like a small region. So what you'll actually see is something more like this. And this is what you'd see in the lab. Now along the y direction is just whatever the laser, just whatever the distribution along that direction of the laser is. And the x direction, we get our sinc function. All right. How about a two-dimensional slit? In other words, a rectangle. Basically, we now have a fully two-dimensional problem, and we have to solve the two-dimensional Fourier transform. But the nice thing about this form, if we look at the form of this function is kind of the product of something along x and something along y. So it's Cartesian separable, it has Cartesian separability. It means we can just write it as an x part and a y part. That means we can just pull out all the x stuff and stuff it into the one integral, compute it on its own. All the y stuff will go in its own integral, we can compute it, and we just get the product of the two things. So this separability is quite nice. So if we have this, we can separate it into the product of two things. We've already done all the work. No big deal. We've done all the work and we get a product of two sincs. Okay? And this is what it looks like. Okay, so if you see that, it looks a lot like the single slit, but if you look very carefully, it's actually two slits. So it's taller. Notice that it's inversely proportional to A. That's how a sinc works. So the taller along y leads to a narrower or a tighter diffraction pattern. And we tried to squeeze it in a lot more along x, and that spreads out the light more along x. All right, but we get this pattern. So for a perfect square, it would be the same. It would just be this grid that had the same periodicity in the x direction and the y direction. Okay, so now how about a circular aperture? This is a very important one, because our pupils are circles and telescopes are circles, camera lenses, that kind of thing. So it comes up quite a lot. So we better deal with this. The problem is doing the Fourier transform in cylindrical coordinates. We don't have Cartesian separability here now, so we actually have to write the Fourier transform in cylindrical coordinates, and it's just a bit more mathy. Okay, so the Fourier transform in cylindrical coordinates looks like this. So before we had x and y, we have kx and ky. What are the conjugate, as they're called, variables here? Well, rho is our x squared plus y squared. That's the distance in cylindrical coordinates, right? You have some rho and some theta, and that's going to have a Fourier pair, which will be also in cylindrical coordinates, and it'll be a k rho, we'll call it, and phi. So these are just the Fourier variables. Instead of x, y, kx, ky, or omega t, we have rho and k, and theta and phi as our conjugate variables. And this is what it looks like. We can exploit symmetry, it turns out, and write this in terms of special functions. So when we have a slit, we could do this integral in closed form. But it turns out when we don't have a slit, we have to use special functions. And we'll leave this to for Pavel to teach you when you take fourth year mathematical physics. But this is actually what is known as a Bessel function. Okay, so a Bessel function is very sine-like. It's like a sine times a polynomial. Bessel function is very, very sine-like. Not exactly. And it's basically comes up a lot when you have problems with cylindrical symmetry. And here we have a Bessel function of x divided by x. It's like a sinc function, but they call it a jinc function. So it's a Bessel function over the argument. The limit, just like in sine, is well defined as rho goes to 0. But it looks almost like a sinc function. but not quite. If you plot them together like radially outward, there's a small difference. But for all intents and purposes, you can think of it as a radially symmetric sinc function. And if you want the hardcore numerical accuracy, it's actually a Bessel function. This is as far as we'll go with that derivation. I was going to make an assignment problem, but then I wrote it out and I'm like, 2 pages later, let's leave this one. So we can discuss it. Let me know if you want to discuss it in class. We can talk about this derivation. But it's just one of these special functions that comes up in math. So we look at the Fourier transform of this circle here, and this is our Jink function, our radial Jink function. It's also known as an airy disk. It's very important because if you're measuring a plane, if you're measuring something very, very far away, what happens when it finally gets to you, whether it's your eyes or your telescope, is it gets, it's basically a plane wave and it gets clipped by the circular aperture of your eye or your telescope. And what you see in the far field, or as we're going to learn next lecture, equivalently in the focal plane of a lens, is the Fourier transform of this circle, which is this airy disk or this Jink function. And the airy disk, the smaller the pinhole, the wider it is. And this is what's fundamentally going to limit our resolution when we look at optical instrumentations. From naive considerations, if you have like a single point emitting light, it should map to a single point. But when we clip something with a circular aperture, it does not map to a point, it maps to this airy function. And that means it's spread out a bit. So if there's 2 very nearby points, they get mapped to their own airy functions and we can't really tell them apart. We're going to deal with this more rigorously a bit later in the course when we talk about instrumentation. Now finally, I just want to say that we've been doing all this analytically in the far field, but I mentioned at the beginning, we can really always calculate the Fourier transform of the aperture function times some overall phase. I just have to include that overall quadratic phase in there, and I get the function at all points. And this is an animation of doing that. So here's an aperture as I move farther and farther away. We get some weird things. If you look very closely, we see that the field in the center of that disk goes to 0 for some distances. And this is kind of a logarithmic zoom out of what happens when we go from z equals 0 to the far field, which in this case is surprisingly 5 millimeters for this pinhole size. But we can see that all along the way, we're going to have these crazier and crazier shapes. In the first few hundred microns or so, we're in what are called the Fresnel diffraction regimes. And it's very complicated to calculate this analytically, but it's very easy to do on a computer. So I'm just calculating these Fourier transforms for different z's away from the source. And this is the function that we get for different z's. Okay, so that's it for today. Let's summarize. So today we introduced the concept of diffraction, and we found that the general property of diffraction is that given a field at some point, we can find the field downstream by this Fresnel diffraction integral. And what that integral actually did is it treated all the points along that source as individual spherical emitters, or which we call wavelets. And we sum them all up, or if there's a continuum of them, we just integrate them all up, and we get what is called the Fresnel diffraction integral. It's a bit of a mess. And we're going to work in the Paraxial approximation. It turns out if we're sufficiently far away, this integral, as we saw, reduces just to the Fourier transform, the 2-dimensional Fourier transform of the aperture. All right, so we've reduced the problem of diffraction to just calculating a Fourier transform. And one thing to note is that the Fourier transform gives you a function in terms of kx and ky, which is really an angular distribution. All right, but we can always get back to normal coordinates just by noting that kx is equal to k theta, which is equal to 2 pi times x over z lambda. So whether or not it's an angular distribution in the far field, it's an easy task to convert between an angular distribution and a spatial distribution. All right, so that's it for today. Next video, we're going to talk about a shortcut to the far field, namely a lens. But that's next time, and we'll see you then.